Now we're going to use these ideas that we have discussed to look at some applications, consequences of these ideas that we have discussed, connection between electric field and potential and so on. So the first sort of application that I want to discuss is a very important one, is a conductor in electrostatic equilibrium. So we're talking about a conductor, and we're talking about the state of a conductor after some amount of time has passed that allow this conductor and the charges inside the conductor to be in equilibrium. Okay? We're not going to be talking about transients, behavior that happens for a short amount of time. We're talking about the long-term behavior of a conductor. So let's say that you have a conductor over here and that you put some charges inside the conductor. I don't know how you did that. You managed to tunnel through the conductor, and in the middle of it you release some charges. Suppose that you can do that. What's going to happen to those charges? Let's say that they're electrons, negative charges. Those charges are going to repel each other. They don't want to be close together, right? So they're going to move out. How far can they get? The limit, of course, is the surface of the conductor. Electrons cannot typically just jump out of a conductor. For them to be able to do that, they need to gain a lot more energy, and that can happen, for example, in the photoelectric effect. If you illuminate with a metal with a particular frequency, with strong enough intensity, you can get the electrons to jump from one electrode to another, collect them with another. But that doesn't happen unless you have these specific conditions. So these electrons are going to move away from each other, and they're going to stop at the surface of the conductor. So eventually you're going to reach some equilibrium where the electrons have moved as far as they can from each other, and the limit is the surface. That's where they will stop, right? Now the question is, what is the electric field inside after equilibrium has been reached? So we let these electrons, give them enough time to settle into whatever position they want to go to maximize the distance between them and the nearest. And the question is there an electric field inside this conductor? The conductor clearly has some net charge. You might expect some electric field. Every time you have charges, net charges, you might expect that. Well, the answer is that the electric field must be equal to 0. And we know that for sure because after equilibrium has been reached, and we're defining equilibrium as the state in which the charges inside the conductor are no longer moving. Remember that the charges in a conductor are not just the extra or the excess charges, but the conductor is filled with charges. Electrons. Metals, right, have electrons that can move everywhere inside the conductor. It's like a gas of electrons. So once the equilibrium has been reached, there cannot be any other possibility but the electric field be 0, because if it was not 0, imagine that there was some electric field left still inside the conductor. What would be happening to the electrons in that region? They would be accelerated by that electric field. They would still be moving in some direction. Okay? And the way they move, they actually tend to cancel whatever electric field is left inside the conductor. We'll see that in the next example a little bit more clearly. So the final condition for equilibrium is that the electric field inside a conductor is equal to 0. That only happens because conductors have electrons or charges that are completely free to move anywhere they want. Alright? Similar situation happens. You don't have to put a charge there to see something like this. You could have a metal, neutral, so no net charges have been added to it, and you place that metal inside, say, a very strong capacitor. So a lot of charge in this capacitor, so you have a very strong electric field between the two plates, going from positive to negative. Once again, the conductor has negative charges that are able to move anywhere they want, So if you look at what would happen to an electron here, the electric field produced by the capacitor is going to accelerate that electron. The acceleration of the electron is going to be in the opposite direction because it has negative charge. So those electrons are going to accumulate on the left side of the conductor. And because we started with a neutral conductor, to compensate for the charge accumulating on the left, for negative charge accumulating on the left, you have to have positive charge accumulated on the right side of this block of metal, right? But notice what happens. What's the result of that division of the charge inside the metal? Well, that charge inside the metal is going to generate its own electric field. You could call that the E internal, and the red one is the external. So notice that they're opposite to each other. The external field is going one way, the internal field is going the opposite way. So that means that they tend to cancel each other. When will the motion of the electrons inside the conductor stop? When are they going to stop accumulating on the left side of the conductor? They would stop accumulating when there is no longer any force acting on them. So the condition is that the equilibrium is going to be reached when the electric field inside is equal to 0. Inside the conductor, you have the electric field produced by the capacitor, and you have the electric field produced by the charge separation inside the conductor. And those two electric fields are opposite to each other. Okay? So once the electric field is cancelled by the internal field, so when you get the net electric field inside is 0, the process will stop. This only takes milliseconds. Once you turn on the electric field of the capacitor, almost immediately the electric field inside the conductor goes to 0 because of the motion of the electrons, which always tends to cancel the external electric field. So notice that the result here is that no matter what you do to a conductor, if you put charges on it, they go to the edge, and inside you get electric field 0. Or if you put the conductor in an external electric field, still it is true that the electric field inside the conductor is 0. Okay, so no matter what you do, that's what you end up having. This is true even when the conductor is not solid, right? Because if you had put this in an electric field, for example, and we say that the charges accumulate this way and that way to make sure that the electric field is 0, the inside part of the conductor is still neutral. So you can carve that out. If it's neutral, it plays no role in the electric forces inside the conductor. So you can take this chunk out of it, and you still have that a metal, even if it's hollow, provided there's no holes, so it just continues, right? You still have that the electric field is 0 when you put this metal in an external electric field. So it's like shielding an external electric field. A solid piece of metal or hollow, think of an elevator, for example, and your cell phone. That elevator is shielding you from any electric field coming from outside. Now that has an implication about the potential on that conductor. If you have a piece of metal, we already said that the electric field inside that metal is going to be 0 when it has reached equilibrium. So what happens when you say you start from point 1 and you move along a path that takes you all the way to point 2? What is the difference in potential between point 1 and point 2? Well, the difference in potential between 2 points is given by the integral of the electric field along the path. Since the electric field is 0, the difference in potential between 1 and 2 is exactly equal to 0, which does not imply that the potential on the conductor is 0. It just implies that it's constant. No matter what 2 points you take inside a conductor, they have the same potential. In particular, the potential on the surface of a conductor is the same as the potential inside the conductor. If you were to measure the potential on the surface, you will know the potential everywhere inside that conductor.